Okay, so I want to talk about how to find the interest you earn and compound it continuously. I'm going to go through this pretty quickly. I'm going to assume you have a little bit of background, but I just want to go back to kind of a basic story. Is if I had $100 of what's called principal and an interest rate of 10%, and I want to say what's my final amount at the end of 2 years. This is how we traditionally had probably would do that. It's like, well, 10% as a decimal is 0.1, and so that's $10. And I add that $10 of what's called interest usually. This is the interest rate. It's usually called the interest onto the 100. So then at the end of 1 year, I have 110. So this is year 0. This is year 1. And then at the I multiply that times 0.10. And so at the end of the next year, I've got $11 in interest, and I add that onto the 110. And so at the end of 2 years, I have $121. That's basically the way interest typically works in what's called a simple interest scenario, where we compound it just once a year. Kind of a quicker way to do that, which most people generally know if they've studied this for a while, is rather than kind of do it in piecemeal, because this is really a problem if you're going out years and years and years and years. If you're doing 2 years, this is not a big deal. But a quicker way to do this is just do the 100 times 1.1. And then if we're going to, for the first year, I multiply it by 1 year. But here's the nice part. If I want to go out 2 years, I just say, we'll do that twice. And effectively what this is, this 1 holds on to the principal. So when I multiply times the 1, I get my 100. And then the 0.1 I've added on is the interest I'm earning. So that's the little bit extra that I get every year. And then if I just do it, if I do that 1 year, it's once. 2 years, I'm going to multiply by 1.1 again, and 1.1 again, and 1.1 again for every year. So this is a nice little thing, such that generally our formula for our amount at the end of some number of years is 1.1 to the x, where x is the number of years. That's for simple interest at 10% for $100 of principal. Okay, moving on. Very often we do what's called compounding more than annually. So once again, we got an annual interest rate of 10%. Generally, you're always given the interest rate in an annual amount. Excuse me, my dog is squeaking his toy in the background, so try to ignore that. If I'm doing it annually, it's still going to be my 1.1. But if I do it semi-annually, what I'm basically going to do is take my $100. I'm going to do 1, but it's not. I'm going to get actually 5% each 6 months. That's what semi-annual is. So twice a year. This is 2 times a year. So I'm going to get 5% twice a year. So I'm going to do it twice for each year. And in this case, I'm still going to do it for 2 years. I want to show what it compares to for the other. So before we had 121, if I do this, it actually comes out to 121.55. Just a little bit more than the 121. Still for the same amount of time. But I got that 5% twice, and every time I did it, it got added on to the principal, so the principal was a little larger each time I did it. If I do quarterly, this is 4 times a year, every 3 months. Okay? So the same idea here. I start with $100. I'm going to get 1.025. So I divide that 10% by 4. I'm going to get that every 3 months. I'm going to do it 4 times a year, but I'm going to do it for 2 years. So I'm doing the 1.025 actually 8 times. And when I do that, I actually get even a little bit more. I get 121.84. So this is pretty good. So let's keep going. For monthly, 12 months, I get 100. If I divide that by 4, by 12, hold on, I need to double check my number here. 1 divided by 12. I think I got my number. Yeah, I'm glad I checked. Roughly 1.083. I was going to write the wrong number. I'm going to do that 12 times a year for 2 years. So it's getting smaller and smaller and smaller, but I'm doing it more and more times. And as you would expect, this goes up to 122.04, a little bit more. Now, this is great. The question is, if I keep slicing it smaller and smaller and smaller and smaller and doing it more and more and more times, well, I eventually get like an infinite amount of money. And sadly, the answer is no. Okay, this is what has a limit, and that limit is kind of interesting, and you can figure this out on your own. And actually, if you want to find that limit, do this like 365 times. do it a daily. Daily is very close to the limit. So if I took 10%, divided it by 365, added it onto 1, did this 365 for 2 years, you'll get something that's about 122.14, very close. So our limit is right around 122.14. So once I'm getting it monthly, I'm not going to get a ton more money, but yeah, extra dime, I'll take it. Okay, so our formula here that we were doing just before, we took our principal, we took 1 plus our rate, so we took our 10%, we divided by 2 or 4 or 12, depending on how often we were doing it. Then we raised it that number of times for every year, and then we multiplied those two numbers together because for every year I'm going to do it that many times. That was our formula for compounded. For continuous, which is kind of our limit, this is like essentially, if you want to think about it, it's every nanosecond. As small as we can split it. It reaches that limit. And so there's a formula for this that basically says if you take your principal, if you multiply it times e, which is approximately 2.718, this is a number kind of similar to pi in that it's got its own symbol for it, and it's very close to 2.718. And I raise it to the r as a decimal, just as like I was using up here, and times the number of years. That will give me the maximum I can get, essentially as if I was compounding every, like I said, the smallest fraction of a second you could compound. So this formula is very useful. And the easy way to do this, the easy kind of problems you typically get is you get some number, you're told the rate, you're told the number of years, you calculate that out. That's dead easy. You know, number times e raised to the, whatever these two numbers are multiplied together. Very easy to type that in your calculator and get it right. Depending on your calculator, you might have to put that in parentheses to make the numbers work out right. Not going to do that. Oh, by the way, e. The log of e, and I'm not going to go into this, is this ln button on your calculator. This stands for the natural log. And the reason it's a natural log is because not only does this work very well with continuous compounding interest rates, a lot of things in nature follow this kind of growth. Because bacteria do not know it's the end of the day, it's time to multiply, or it's the end of the quarter, it's time to multiply. They just multiply essentially continuously. So they follow this pattern as opposed to this kind of mandated pattern. All right, now that might be useful, it might not. You do have a natural log. A lot of times students will say ln, but you have a natural log button on your calculator, and probably right above it, kind of using the second key, you'll have the e. On my calculator, I've got ln, and right above it, I've got e to the x is the second key, because those are inverse functions. Okay, last problem and we're done. So this is a harder problem that makes use of this. And actually, essentially, you can get a similar kind of problem with compounding continuously, but the hard thing to figure out is the t or the r if you're given everything else. So it doesn't matter which one I'm calculating, but in this situation, I've got $50. I would like to double it in 10 years, so I'd like $100 in 10 years. Question's what's the rate? Okay, so the first thing we do to make this simpler is we divide by 50. Okay, so I've got 2 equals e to the r 10. This is where you have to know something about logarithms, or I guess if you wanted to, you could put this in your calculator, and if you got a calculator that does tables, you could find where it's equal to 2. But a couple of ways to do this. I'm going to take the natural log of both sides because those are inverse functions. So I'm going to take the natural log of this side and the natural log of this side. Okay? And there's two ways to think about this. Our powers rule says that this can come out front, so I can bring the R10 out front of this thing. So actually it didn't matter if I used the natural log, it would work with the regular log. And then actually the log of e is actually 1, so it'd just be R10 on this side. The other reason it's R10 on the side is these are actually inverse functions. E to the something and log e are inverse functions in the same way that log 10 and 10x are inverse functions. So any way I cut it, I'm going to end up with R10 on this side, and this is what I like to call an algebra 1 kind of problem. Okay, now I've just got some number equals my missing value times some number. So I divide by 10, and I don't know what the natural log of 2 is, so I put it in my calculator, and it's roughly 0.06, I think it was 9 Or was it 3? Hold on, let me see if I still got it in my calculator. 6.9. So it's about 6.9%. So at 6.9% interest rate, compounding continuously, I can double my money in 10 years. If I was doing it compounding something less than continuously, it's still going to be in this neighborhood, but it's going to be a little bit more because continuous is faster than compounding semi-annually or quarterly or daily even. All right, ciao.